Hi, I'm Sia Arabandi, and this is my physics lab on constant velocity. Here's a quick overview of everything I'll be covering during this video. The purpose of this lab is to observe the position of some object that is moving at a constant speed without changing direction and to compare this motion to the predicted position of the same object, calculated by a computational model. Here I'll be using a pickleball as my object, and I will record observed position using tracker and predicted position using GlowScript, and this lab will help demonstrate the principles of Newton's second law. Here are some physics principles that are relevant to this lab. Newton's first law states that an object in motion will remain in motion at a constant speed and a straight line, and an object at rest will remain at rest unless acted upon by an unbalanced force. Newton's second law relates the net interaction between system and surroundings, which is the net force, to the observed motion or changes in momentum of the system. Here, the formulas relevant to this lab, specifically Newton's second law and the derived formulas, are shown below. These will be used in the computational model to predict the position and velocity of the object as a function of time. Here is a description of my procedure during this experiment. I will roll a pickleball, which is my system, in a straight line at a constant speed across the table, where the environment is my surroundings, and I will record the ball's motion. Using Tracker, I'll record the ball's frame-by-frame observed position, and then I will create a computational model of the ball's predicted position over time using GlowScript. I will then compare the observed and predicted motion by plotting both positions over time on the same graph. Let's discuss my experimental observations. Here is my tracker video of the pickleball moving at a constant velocity, where I inputted the center of mass at each frame so we can record the change in position over time. I chose the right axis to be my positive x direction because that is the direction of the ball's motion. The position versus time graph generated by the tracker is pretty linear, showing constant velocity, and has an upward slope. Now let's analyze the data in our tracker. The total time of constant velocity of the pickleball from the start of its motion to the end is about 0.8 seconds. The initial position of the ball was approximately 0.112 meters in the positive x direction, recorded from the tracker table. From these constants, we can find the initial velocity by taking the change in position over the change in time during one frame, giving 1.212 meters per second in the positive x direction. These three initial constants are inputted directly in our computational model. Here I inputted the initial position and velocity that we found using our tracker data. I also inputted the mass of the pickleball, initial time, and set delta t to 1 over 30 since the video was at 30 frames per second. Let's look at our calculation loop. Here, I set t to less than 0.833 seconds during our while loop because the final time of the ball when it stops its constant velocity motion was 0.833 seconds. I also set the net force to a zero vector since we are trying to achieve constant velocity. Then I inputted the velocity update formula and the position update formula to predict the position of the ball. Since net force is zero, the ball velocity is set to an initial ball velocity, which will result in a constant velocity over time. Due to this constant velocity, we will see a positive, steady change in position over time. Let's look at our observed versus predicted position comparisons. Here in this graph, the red dots represent the tracker model graph, and the blue dots represent the computational model. As time goes on, the actual experimental position diverges from the theoretical position calculated by our computational model, which means that there is some external force that slows down the pickleball over time in our experiment. The computational model, on the other hand, will enforce constant velocity at all times. Let's discuss possible sources of error in our experiment. One source of error could be outside forces like friction and resistance, which cause us to not maintain a constant velocity during our experiment. There could also be human error when I mark the positions by hand on tracker, or rounding errors in finding initial conditions for computational models. If the axes were flipped, my results would not change. The only difference would be that the slope of the graph would be negative instead of positive. This is because the object would be moving in the negative x direction rather than the positive x direction over the same period of time, so the magnitude of the position would remain the same. Can we determine the number of pushes and pulls on the object to give a net force of 0? No, we can't determine this number because although in this experiment we attempt to maintain constant velocity, we cannot prevent external unbalanced forces acting on the ball. In this case, friction causes a change in the ball's velocity over time. Thus, the experimental net force is not zero. However, since we set the net force to zero in the computational model, it overestimates the position over time graph since it assumes velocity is constant. Thank you for listening.